Okay, digital communication, lecture 3.1. So we're chapter 3 on digital communication and low-level I/O. Okay, so that's what the lab exercise will be geared towards this week, lab 3. And so we'll do some introductory lectures, and then we'll go over the lab exercise. So digital communication. Digital signals convey information via a communication channel, which is a wired or wireless means of transmitting and receiving electromagnetic signals over some distance. In embedded computing, most digital communication channels are wires and buses. An example of a bus is the familiar slot on a PC motherboard, as shown in figure 3.1. So who out there has installed something in one of these PCI buses on a motherboard of a PC? Okay, decent number of you. So that's a computer bus, and that's one of the main ways that signals are communicated in the PC world. There are two primary divisions of digital communication: serial parallel and synchronous asynchronous. So sort of like 4 quadrants of types of communication. These divisions are explored in the following sections. Afterward, common communication protocols are described. So, serial and parallel communication. Communication can be in serial or parallel, with the former taking place sequentially over a single channel and the latter over multiple channels, as shown in figure 3.2. So here's that figure. You have a transmitter in serial communication with the receiver, and you see there's only one channel here. Everything has to go through that one channel, and it just has to, it has to pile up at the transmitter, go through one at a time, okay, over to the receiver. Parallel communication, the transmitter and the receiver have multiple channels between them, and there can be multiple bits of information conveyed at the same time. Okay. Serial communication transfers each bit of information at a time and has significant advantages for long-haul communications. It's only a single channel is required to span the distance. Okay, so it's nice if you're going to run a cable 100 miles to only have to run one cable instead of 8 cables. So that's one advantage of serial communication. Parallel communication transfers several bits in parallel, which can be faster than serial communication because you've got multiple going at the same time, but has the disadvantages of clock skew. So in synchronous parallel communication, arrival of supposedly simultaneous bits can be skewed in time. So that can happen if even like the lengths of the wires are slightly different. Okay, and serialization, deserialization. So converting parallel to serial and vice versa. However, recently improved serial communication speed has given it the advantage, even over short distances. For instance, the parallel PCI bus of the figure above, 3.1, has been largely replaced by the serial PCI Express bus. So this is something that's kind of out of date. It's parallel, and it's been mostly replaced by something that's serial. So you guys have seen the PCI Express buses as well, probably, if you've installed those hard drives and looked in there, blown the dust out with a little canned air to see what's going on inside the chassis. You've seen these guys on there. So somewhat counterintuitively, things have actually moved more in the direction of serial communication instead of towards parallel, which computing on the processor level has gone the parallel direction instead of serially done. So that's that division. So between serial and parallel communication. The other division is synchronous and asynchronous communication. Synchronous communication and there should definitely be a U in there, is that for which a common external clock times both the transmission output and the receiving input. Okay? So the clock, usually a digital signal itself, signifies when the signal at the receiver and is valid and should therefore be read. Okay, so it says read now, read now, read now, read now, read now. And so that's synchronous communication. Asynchronous communication encodes the starting and stopping information in the bit stream itself. So the receiver detects a start bit, waits a predetermined amount of time, reads the next, often 7 or 8 bits as data at a predetermined constant rate called the bit rate or baud rate. There's a slight difference, but we'll ignore the difference. Often reads the parity bit, which we'll talk about in a second, and finally the stop bit. So you have to kind of encode that the start and the stop into serial communication, whereas in parallel, in synchronous communication, you don't have to do that because you just tell it, read now, read now, read now. So synchronous and asynchronous. The parity bit is used for error checking, for which there are 2 general forms, even and odd parity. In even parity, the transmitter sends a parity bit of 0 if the number of ones in the data is even, and 1 when it is odd. Okay, so it's like, hey, I'm going to send 7 bits of information over, and if you're using even parity and the number of ones is even, then it sends a 1. It sends a 0, and 1 when it's odd. Even parity takes the opposite approach. Did I say did odd first, didn't I?
You said even twice.
Oh, I said even twice. This means this is supposed to be odd. Haha. Odd parity takes the opposite approach, with evens getting 1 and odds getting 0. This lets the receiver check the parity of the received data. Of course, if an even number of bits are incorrect, checking the parity bit will not be sufficient for error detection. So it's trying to say, okay, I received this. I know that we're using even parity, so I'm checking to see if, in fact, the parity is as it was sent to me. And if the answer is yes, you can feel pretty confident that you have the correct transmission. However, if there happen to be 2 errors in your reading, then that parity bit will still check out. So it detects 1 error well, it detects 3 errors well, it detects 5 errors well, but the even number of errors, it doesn't do so well. So that's a little bit about the parity bit, why we use it, and how it gets sent. So standards. So communication standards define signal, electrical, connector, cable, and other characteristics that can be adopted across an entire industry. For instance, USB, Ethernet, and RS-232 are such standards for serial communications. The IEEE, Institute of Electrical and Electronics Engineers, defines communication protocols for many wired communications, and the ISO, the International Standard for Standardization, defines several others. So, like for instance, the Ethernet ones, there are several subtypes of IEEE 802.3, and they have all these characteristics, like this amount of voltage, the amount of time that is in between each bit that's communicated. All these things are defined. Otherwise, all you would see is just a voltage changing on a line, or like if you have multiple channels, a bunch of different voltages changing, and you have no idea how to interpret it. So if you know that it's using a certain standard, like the USB standard or the IEEE 802.3 standard or the RS-232 standard, you can then interpret what it is you're receiving, and you'll know how to receive the data that's coming in. Okay. You'll also know how to send it over such lines so that other people will be able to understand it. If you use non-industry standard protocols, then yeah, then what you're doing is you're locking the community in. If they use your product, they have to use your special peripherals as well. And so it sounds great if you're trying to build the thing where like everybody has to buy your stuff, but it's not great if you want somebody to be able to hook up their printer to your computer that you're designing, because then that printer is going to use some standard and your computer uses a different standard. They're not going to work together, right? So it's a good thing, these standards. And there's IEEE did FireWire. USB is not IEEE, but it's similar. RS-232 is a pretty old one for serial communication, but it's still used down at the computer level, down at the board level. And there's still serial communication like RS-232. So, and you can get RS-232 to USB converters and stuff. Not all these standards really convert well to each other, but some of them do. So these standards are there to help us design things to transmit and also receive information over networks. So this could be something that's on the board, maybe integrated circuit that you have on your board that you've designed. It could also be something that's a peripheral device like the LCD screen or the keypad that we're using. So they have certain standards that they use for communication. Okay.